Okay, well, welcome back. Um, as always, this is E443, 543. This is our third lecture. I need to remind people that we are live streamed on YouTube and recorded. So for today, I had put in a certain amount of review material. And so I'm going to review some of the things we covered last week a little bit, maybe with a slightly different perspective. And then we're going to do some more exercises on adhesion energy, contact energy, and then we'll come back and redo the self-sorting problem. Maybe do a little bit more on that in class. Okay, so last time we talked about how the universe is represented inside of CompuCell. And the key thing that we have to remember is that there is a lattice, and that lattice represents the universe that our cells and our eventually chemical fields will live in. And we typically use a simple rectilinear Cartesian coordinate system. In fact, we don't really have any significant options on that one. Doesn't have to be square. It could be rectangular. It could be two-dimensional or three-dimensional. And CompuCell does provide some features so that if you want to change the size of the lattice while the simulation is running, you can do it. But to be honest, I've never tried that. I know it is supposed to work. If somebody wants to try that, it would be interesting. Something that we do have to think about a little bit, and we've talked about in a fairly casual way so far, but when you start digging into using CompuCell, it's going to become a bit more of an issue, is that you'll hear discussion of things like nth order neighbors, nearest neighbor, second neighbor, third neighbor. And CompuCell also supports both square and hexagonal lattices. And you could say, well, why bother with a hexagonal lattice? Square lattices are fine. Some of the calculations we do are better behaved on hexagonal lattices. And so one thing that's nice in CompuCell is you could switch with a single tag in your XML, switch from a square lattice to a hexagonal lattice and see whether it makes a difference to your calculations. But the neighborhood adjacency, neighborhood range is something that we have to think about. The homework talked about that a little bit. And so if we are in two dimensions on a square lattice, a voxel, in this case a pixel, has four nearest neighbors, which are labeled 1, 2, 3, 4, ones here. It has four additional second neighbors, four additional third neighbors, and then 8 fourth neighbors. And you could ask, why do we need potentially to go to longer range interactions? And the answer is that being on a lattice has some peculiarities, geometrical peculiarities, which were addressed in that extra credit problem that was due today as an optional problem. And those peculiarities become less when you make the interaction ranges longer. A hexagonal lattice looks like this. A voxel has 6 nearest neighbors, and then 6 second neighbors. And as you go out, you see that it has sort of a different structure. I don't know if people have ever done hex lattices on before computationally, but actually a hex lattice is easy to do because if you take a square lattice and imagine joggling every other row back and forth by 1/2 voxel, that gives you a hexagonal lattice. And so you actually, a square lattice maps onto a hexagonal lattice without changing the data structure. You change the adjacency list, but you don't actually change the data structure. So for fancier lattice architectures or going off lattice, things like tetrahedral decompositions, you have to then go to a linked list data structure. But a hex lattice you can implement just using an array, a square or a 3D array. So you don't need to do anything fancy. We've seen how to define the lattice in Wizard. That's in that first screen after you've named your file. You have the lattice dimensions X, Y, and Z. So far, everything we've done has been two-dimensional, but you can change that Z thickness to be something else to make it more dimensional. The one option you're always going to have, we haven't also played with that, is you can decide whether your lattice boundaries are no flux, essentially rigid boundaries, or periodic. Now, of course, in reality, your experiments don't have periodic boundary conditions, but the walls of the simulation having no flux boundary conditions, we're going to find that makes things stick to the walls. And so sometimes it's convenient to be able, if you have, say, a cell that's crawling around, to have periodic boundary conditions so that the cell doesn't get stuck if it crosses the edge of a simulation. And you see under that lattice type square, you could pull hexagonal down if you want. And then the next one is that membrane fluctuation amplitude, what we call temperature. The next one, pixel copy range, is that range function that I've just discussed. And the default is 1, and we've left it at 1, but I typically will use 2 or 3 in that placeholder. You'll see the consequences of that a little later in the class if we do that exercise. So those are things that you might want to review in terms of using CompuCell and relating it to what you know. If we look in the XML, we flashed the CompuCell language, model specification language, the XML, a few times. I haven't really walked you through it in detail, but in the XML, there's a block that has the name POTS. As usual, the naming is obscure, is for historical reasons. It might be nicer if it were called something like Lattice rather than POTS, but it's called POTS. And there's a tag that says dimensions X, Y, Z. Another tag that says steps, that's how many Monte Carlo steps the simulation runs. Typically, we'll make that a large number and then stop the simulation by hand, but sometimes if you're running on a batch mode, you'll want to stop the simulation after a fixed number of Monte Carlo steps. That fluctuation size, which is labeled temperature here, neighbor order, that interaction range, here it's listed as 3. I showed it as 1 in that previous slide. And then whether your boundaries are periodic, and you can have that be separately periodic in X, Y, and Z. We talked about cells, and a cell lives in the cell lattice. Cell lattice is a bunch of integers. Each cell has a unique identifier, integer identifier, and all the lattice sites with the same identifier are part of that cell. So all the lattice sites that are labeled 1 are part of cell 1. All the lattice sites that are labeled 2 are part of cell 2. They don't have to be connected. If I have separated voxels that are labeled 2, they're all part of the same cell. By default, there's a 0, which points to is called medium, which is what happens when there are no defined cells. And medium has somewhat strange properties. In particular, it's lacking certain properties. Again, there's a bit more or less historical reason for this. If you have cells that are very large, the parallelization algorithms that CompuCell use have some difficulty. And by making medium is actually a null object. That means you can't attach properties to it, which can be a little bit annoying. On the other hand, it also makes parallelization of the software a lot easier. So one thing that we're going to come back to that was in the homework was that cells by default, by definition, have a volume because the voxels they occupy belong to them. They're objects. But the surface of a cell is a fiat object. It's not an object itself. It only comes about because of a voxel being next to a voxel of a different cell. And so surfaces are not objects in a CompuCell world. So this is really just a summary of that. By default, cells have a volume. They have a surface area associated with them. It has a type, which we could think of as a cell type, although we can use it more generically to denote any kind of classification, just the way the cell, we often call these things generalized cells because they really represent volumes of material. That volume of material could represent a real biological cell. It could represent a region of a biological cell, like its apical surface or basal surface. It could represent a structure inside the cell, like the nucleus of the cell, or it could represent something more abstract, like a volume of fluid, if we wanted, or a volume of a solid material. But in any case, cells come packaged with volume, surface area, and type. Those are intrinsic properties. And we talked last week quite a bit about the idea of specifying cell behaviors and interactions using this effective energy formalism, and the fact that that's really equivalent to a force-based formalism, which is probably more familiar to people as physics. Each one of these energy terms or effective energy terms corresponds to what's called a plug-in computationally. One thing that we have to get used to, which I introduced last week, and I want to come back to because it's a concept that's often a little bit, it takes a little bit of getting used to, is the fact that things like cell volume and cell surface are results of the simulation. And therefore, the simulation will specify target values, target volume or target surface, and then some constraint strength on that property. And the actual volume and surface then will be a result of the interactions that those cells undergo. And again, I gave the example of taking a bunch of balloons. The balloons have some volume if they're sitting by themselves. If I squish them together, their actual volume will be smaller than what they would have if they were uncompressed. And so we have to think about what those mean. The strength of the constraint, which we'll call lambda volume or lambda surface, correspond conceptually to the mechanical compressibility of the material, the inverse compressibility of the material, the Young's modulus in this case. The reality would be that cells are not very compressible. Physics will teach you that fluids are, quote, incompressible. In actuality, cells have some compressibility because if you squeeze on a cell, you have fluid that's transported out of the membrane. And so cells are somewhat compressible, but not very. There's a classic ancient way to split rock, which the Egyptians used, for example, which is if you drill a small hole in a piece of granite and you put beans in it, and you then pour water on the beans, the force of expansion from the water in the beans is enough to split the rock. So cells can be pretty incompressible under certain circumstances. Okay. Terminologically, if the actual volume, whatever it is equal to its target, we say the constraint is satisfied. That's terminologically. Again, I made the analogy between loss functions if you're doing neuroscience. Sometimes in some fields they're called penalty functions. In our case, we're calling them effective energies because it's coming from physics. And so typically the constraints that we're going to write are going to be what are called elastic. That is, the effective energy increases as the square of the distance from the constraint satisfaction. And that has the result that quadratic form here means that the force is linear. In physics, that's called a Hookean spring or linear elastic model. That is, the further away we get from being constrained, the stronger the force that's pulling us back. And so if we think about a spring and we pull away from the spring, there's a restoring force that pulls us back towards the satisfaction of the constraint. If we were in a Newtonian system with no viscosity or no damping, then the system would oscillate around its target. That's not what we want biologically, and doesn't correspond to the physics. In this case, we're in a damped or overdamped system so that the system will restore without. The picture I have actually shows the spring a decaying oscillation. Uh, what we want is for the system to reach its equilibrium without oscillations. And so we're in a damped system. But the key thing here is that last equation on this slide, that the force is proportional to the, here I've used K because physicists use K for spring constants. In our world, it would be lambda times the value, in this case, the length of the spring minus its target. So when I pull on a spring or a rubber band, the restoring force increases linearly as I stretch the spring. Okay. If I wanted to compare things to Newton's law, I'd have the second derivative, the acceleration, is equal to 1 over the mass times the restoring force minus gamma, which is the damping, times the velocity. Again, in an introductory physics course, you tend to use Newtonian mechanics without damping. Maybe people, if you've taken a little bit more physics, have done some math with damped force velocity relations. This basic concept of a spring pulling things back, it seems very concrete, but it's actually in the world of our simulations quite general. Almost any behavior or interaction can be written in the form of a constraint. And the nice thing about the particular dynamics that we've defined on the system is that it will automatically satisfy, the system will evolve to automatically satisfy any constraint. And so this constraint could be get bigger, get smaller, change the ratio of your surface to your volume. All of these could be written in the form of constraints. Now, if we have multiple constraints acting simultaneously, we can't satisfy them all at once. And so what we'll do is we'll satisfy some average of these constraints. And the stronger the lambda, the strength of each constraint is, the more we satisfy that one at the expense of its competitors. Right. Again, the key thing to remember is that the force on an object from a constraint is -2 times the lambda for that constraint, the strength of that constraint, times the value of the constraint, the value of the characteristic of the object related to that constraint minus the target for that constraint. Again, so you have a linear force in terms of distance. Before I move on, one thing that is important when you're doing this kind of work, and again, if you think of forces, it would also be true. If I have an elephant and a gnat pushing on the same object, the elephant is exerting a lot more force, and the effect of the gnat is not going to be significant. And so when you build simulations with a lot of energy functionals in them, you need to tune them so that the effective forces are roughly comparable from all of the different contributors. Otherwise, the ones that are small won't do anything. Now, biologically, that may be correct. In other words, there might be a force that's present, but so small it's not something you have to worry about. But in general, if you have something that's so small you don't have to worry about it, you can ask the question, why would you include it in your model? So that's something to think about. Okay. We've talked already about the two most important constraints we're going to run into, cell volume and cell surface area. Most cells, in fact, almost all cells have defined volumes or target volumes. And so in this case, the constraint has the form of lambda volume times the actual volume minus the target volume quantity squared. This is exactly equivalent to the ideal gas law, if you're a physicist. And lambda volume is the inverse compressibility of the Young's modulus of the material. The pressure, there should be a 2 there, is 2 times lambda times the volume minus the target volume. And that's not a bad approximation, actually, the way osmotic pressure works in cells, in real cells, except for the fact that lambda is much smaller than the real one. So our cells are going to be compressible. They're going to be softer than the real cells. And one of the reasons that this simulation method works, numerically is pretty stable, is that squishiness. It also has a slightly perverse effect that the speed of sound in the material is slow, but that's something we'll come to in a little bit. Surface area, if we constrain it, has the same form, lambda surface times the actual surface minus the target surface quantity squared. Surface to volume is a little problematic. If I have a geometric shape not on a lattice, and this is a homework problem, a geometric shape not on a lattice, and I take the ratio of volume to the 1 over the dimension of the system, that would be 1 over 2 or 1 over 3, divided by surface to the 1 over d minus 1. So for example, in 2 dimensions, it would be volume to the 1/2 divided by surface. In 3D, it would be volume to the 1/3 divided by surface to the 2/3. That number is a geometrical factor that describes the shape of the object. The minimal possible R would be for a sphere. And then actually I've got it defined upside down. So our surface is on the numerator. So the biggest possible value of R would be for a sphere. And that would get smaller for more complex shapes. And CompuCell doesn't let you define that R value. You have to keep that adjusted by hand. Morpheus lets you define R, which is a little more convenient. If we look inside of the XML in CompuCell, we have to do a couple of things. We have to list our cell types. And so there's a block in our XML that says cell types. Here, plug-in name cell type. We always have cell type 0, which is medium. We can't change that. And then we have cell types. And those type IDs are a little bit of a holdover from old versions of CompuCell. Typically, we'll use the type names instead. If you want to create any cells, you have to have at least one cell type defined beyond medium. And then the volume, target volume is specified here by something called volume plugin. And we say volume energy parameters. You say which cell type, and then lambda volume, and then the target volume. Now we're actually going to find that for a lot of the things we do, we want to be able to have different cells of the same type have different target volumes, or we want to be able to change the volumes of the cells in time. And when we do that, we're going to define those lambda volume and target volume in Python instead of in the XML. So we'll see a slightly different syntax a little bit later. If we want to be able to change those parameters while we're running the simulation on the fly, then that model editor window only works for the XML variables, so XML parameters, so it's convenient to have it there. Okay. Surface area is a little bit problematic, as you found out in the homework. In particular, that ratio that I just defined, that R ratio for a given shape, changes as you change the size of the object on a lattice, which it doesn't do in the real Euclidean world. And so using that target surface area requires a little bit of care, which is why we had the homework problem to analyze. Another thing which you've heard me say before, and I'll come back to, is that CompuCell doesn't give you very much for free. In the real world, we get physics for free. If I have 2 robots that are running around and they bump into each other, something will happen. Computationally, unless I assert some properties of the system, they're not there. Uh, if we don't define a cell lattice, the simulation doesn't have a cell lattice to put cells in. If we don't define cell types, there are no cell types. If I don't create cells to instantiate a given cell type, there aren't any cells. And those cells don't have any property unless we define them. And we actually saw that on day one, where I forgot to check one of the boxes in the wizard. So our cells didn't have a target volume, and they all disappeared. And the only reason cells exist or continue to exist when we run the simulation is because their properties of their effective energies are encouraging them to do that. And so we have to remember that we don't get much for free in this world. We have to define it. We have to build the systems. So one of the things that that homework problem was about, the two homework problems for this week were about, was that being on a lattice, especially because we're on a lattice that could be square or hexagonal, it could be two-dimensional or three-dimensional, it could have a different interaction range. We're allowed to change all of those things. We have to develop a little bit of familiarity with how those lattices behave. And the homework assignment was essentially to do a little bit of that. And so let's suppose that we have a cell and it has cell index sigma. I've shown a picture here of a cell in red. And all voxels of cell index sigma are red in this diagram. And one thing is that distances have strange properties because we're on a lattice. It's what's called the Manhattan metric rather than Euclidean distance. In the old days, people in this class are probably too young to remember, Scientific American had a column called Mathematical Games, written by somebody named Martin Gardner, who was a very famous, popular mathematician. And there's a very good article in the Mathematical Games column on Manhattan metrics and all of their perversities, I think from about 1982 or 1983. So it might be actually worth having somebody dig that out and distribute it to the class. Distances don't behave the way you might expect. And we also have to deal with the fact that we can change our adjacency rules. And CompuCell internally has something called a neighbor list, which says that if I pick a voxel, who are my neighbors? And that neighbor list will depend on whether I'm 2D, 3D, square, hex, periodic boundary conditions, or fixed boundary conditions, and on the range of interaction that I've defined. So let's pick a voxel. We'll call it 0. And now let's find its nearest neighbors. There are 4. And those are pretty easy, up, down, left, right. That's our nearest neighbor adjacencies. If I go to second neighbors, I add the upper left, upper right, lower right, or northeast, southeast, northwest, southwest. And CompuCell actually doesn't do something which it probably should do, which is that when you calculate forces, forces are energies divided by distance. We calculate a change of energy, but we don't normalize it by the copy distance. And something I would love somebody to check would be what would happen to our simulations, whether they'd behave better if we actually normalize the force by the copy distance for this. Third neighbors goes out again, basically jumps in our first direction again. The third neighbor interaction doesn't give us much. It doesn't smooth things out very much. There are 4 of them. And then if we go to fourth neighbors, we get something that's a little bit more round, adding those 8 fourth neighbors in that range there. So we have 4 first neighbors, 4 second neighbors, 4 third neighbors, and 8 fourth neighbors. If we were in 3D, how many first neighbors do we have? 6. Thank you. So Emma says 6, which is right. The calculations in 3D for the nearest ones are pretty easy. For example, if we went to the second neighbors, we basically fill in the cube. When we go to longer distances, some of those shapes get a little bit complicated. So here's the 3D case. The nearest neighbor gives us one plane above and one plane below, so it has 2 more neighbors that we have to worry about. If we go to second neighbors, we get the diagonal ones in the plane we're in, but we get 4 and 4 in the top and bottom plane. So we actually have 12 second neighbors. So in the nearest neighbor, so nearest neighbor in 2D we have 4, in 3D we have 6. Second neighbors in 2D we have 8, in 3D we have 12. So you can see they're not scaling in the same way. I'm not going to do third neighbors in 3D. You could look it up. Hexagonal lattice is a little bit different. Hexagonal lattice, as I mentioned, is a square lattice with extra adjacencies. And the way the extra adjacencies work is that in even rows of your lattice, to north, south, east, west, you add northeast, southeast. And then in odd rows, you add northwest, southwest. So the lattice adjacencies are different in even and odd rows of your lattice. That's actually not hard to implement computationally, but it does require a little bit of getting used to, and it builds that zigzag that you're seeing here. It also means that a boundary that's straight in one direction, 13, 14, 15, 16, 17, 18, straight line in a square lattice is still a straight line in the hex lattice, but a vertical line, 27, 21, 15, 9, 3, becomes a zigzag on hexagonal lattice. And so there are a little bit of you can have it's a little bit can be a little bit confusing to deal with hex lattices. And when you have periodic hex lattices, you have to be a little bit careful, because if you have the wrong number of lattice elements, the hex lattice could become inconsistent when you try to do periodic boundary conditions. So here's adjacency in a hex lattice, drawn as a square lattice, because that's how it's implemented. So the nearest neighbors to our voxel 0 here would be up, down, left, right, and northeast, northwest. I said northeast and southeast, sorry. If I'm in an even row, and if I'm in the row below it, they would be northwest and southwest. So you see that the adjacencies would be different depending on what row of the lattice I'm in. When I go to 3D, the adjacencies get a little bit more complicated. Maciek was very proud of working out the mathematics of the 3D hex lattices, and he's got a little manual online if you're interested about how that works. It does mean that distances get a little bit strange in hexagonal lattices, because if the northwest in a square lattice, the distance from the center to your nearest neighbors is 1. To the second neighbor, it's square root of 2. In a hex lattice, all of those distances have to be defined as the same. And so it means that the volume and lengths that you measure in hex lattices are a bit complicated. And so calculating, going from lattice counts to distances in hex lattices is a little bit complicated. Maciek talks about that in the manual. volume is a pretty straightforward concept, as I mentioned, because every cell is labeled, and therefore you count how many voxels there are with that label. So here I have voxel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on. And so it's sort of an embarrassing in-class exercise, but what is the volume of my red cell? I get 21. Surface area is a little bit more complicated. So surface area is defined as the number of edges with a mismatch between the voxels on either side. And so here, let's look at voxel 0. Nearest neighbor, it has two mismatched nearest neighbors, which are labeled 1. And therefore, that contributes 2 units to the surface area. The voxel down here in this middle one has 1 mismatched nearest neighbor unit, and therefore it contributes 1 unit of surface area. This voxel here at the bottom right has 3 mismatched neighbors, so it contributes 3 units to the surface area. You'll notice that the same mismatched neighbor can be counted multiple times because what you're counting is the number of faces or edges that are mismatched. Now, I didn't know until last week that actually CompuCell allows you to calculate the surface area with longer ranges than this. Maybe it's a good thing that I didn't know that, because you would have gotten a harder homework problem if I'd done that, because counting to second neighbor and third neighbor for mismatches is a little bit more complicated. But it's possible to do that. What CompuCell doesn't do is it doesn't automatically scale things like the surface area computation based on the neighbor range. If I go to third neighbor, the same shape is going to have a bigger area when I do my counts than if I do nearest neighbor. And you can get a rough idea of what that scaling should be, but it's not exact. It depends on the shape. The reason we don't do that automatically is because the correction only depends on the details of the shape. Pedro.
Is there an advantage of using higher neighbor order to calculate surface in terms of smoothing out the cell edges?
So Pedro asks, is there an advantage to using a higher order neighbor when you're calculating surface area rather than using nearest neighbor? And the answer is yes. When the surface area has some pathologies associated with the lattice, especially square lattice, 2D square lattice, and those pathologies are less severe when you go to higher order neighbors. And so there's some advantages to doing higher order neighbors. There's some perversity of doing higher order neighbors too, because you can jump. Suppose you have a very thin cell that's 1 voxel thick between a cell and another part of the same cell, then your nearest neighbor is going to be different. You'll count the edge right, but you go to second neighbor, you're back inside of yourself hopping over something else. And so there could be you could get some artifacts where you'll get striped patterns, one voxel thick striped patterns simulations.
It starts becoming non-local.
So Pedro says that, of course, going to higher interaction ranges effectively is making your system less local, which is true. In a sense, you're getting closer to a center model type approach like Paul's physicell, where you have some kind of interaction range and interaction potential. So you have to decide for your particular problem what the trade-offs are. If your cells are very large compared to the defined interaction range, then there isn't a problem. If your cells are 4 voxels across and you define an interaction range of 6, then every voxel is a surface voxel. for example. And that's life when you use a lattice approach to simulation. Actually, you have some of the same things happen even off lattice, so I shouldn't be too hard on the lattice methods. So our exercise 3.0.2 is what's the surface area of the red cell, assuming we're nearest neighbors. Anybody want to give that a shot? For me, the problem is always finding a point where I can start to count, because otherwise I forget where I started. I think I got 26.
Huh?
I got 26.
26? Yeah, 26.
Maybe I skipped.
Wait, because you see that there is 12 here, 12 here, 12 here. Yeah, 26. Yeah, that's right. Yeah, 26.
It's certainly possible I miscounted the number of edges, but those are all the edges. And I think it's 26. Okay, so we did this so now that we've counted the actual volume and the actual target area, the actual surface area, we can ask the question in the homework, given a given target volume and target surface, what are the energies associated with those? And so to start with, if we have a volume constraint and the target volume is 25, I say, what's the effective energy of the image? Well, now I have to count how many voxels there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So V is 21. V target is 25. 21 minus 25 is minus 4. Minus 4 squared is 16. 16 times, and lambda volume is 2, so 16 times 2, it's 32. So the effective energy of this image is 32. So now the second question is, what is a single voxel change to the lattice configuration that would reduce the volume constraint energy? Does anybody have a proposition? What could I do to this pattern that would make the energy smaller? I'll give you a hint. Is the actual volume less than or bigger than the target volume? What did we count? How many lattice sites do we have? 21. So the lattice, the volume was less than its target. So how do we reduce the energy? Emma says increase the volume. So if we add one red voxel anywhere in this pattern at all, we will decrease the energy. How much will we decrease the energy? Well, we've gone from 21 minus 25, which is 4, to 22 minus 25 is 3. So our energy is 9 squared, because it's the difference squared. So it's gone from 16 to 9 times 2. So we've gone from 32 to 18. So we've decreased the energy. 32 minus 18 is by 14. Okay? It takes a little bit of getting used to. Once you've done it, we're doing arithmetic. I mean, all we're doing is simple arithmetic here, but we're not used to doing those calculations in our head, probably. Maybe if somebody is, I congratulate you on having done it in your head before. But if you haven't worked on lattices, you're not maybe used to this. Okay, what would a lattice configuration be that has 0 volume constraint energy? Santu, can you answer that? I remind people who are online that if you're going to be online, you have to be there to answer questions. Jonathan?
So I had to unmute for the total surface.
Well, we're in the volume here. So if I,
Or yeah, sorry, volume. I was
this
looking
in
at
a
the
sense
next
is an
problem as
easy,
well.
this is an easy one.
Yeah. So to bring it closer to target, you would remove one
So
or add one rather.
right. So adding one makes it closer to target, but if I want the energy to be exactly zero, what
Just
do I
make it
have to do?
equal so that you
Exactly.
would cancel everything out. So 25, which is our final target.
Right. So if I added 4 red voxels anywhere in my pattern, it would make the volume energy 0. Exactly. Thank you, Jonathan.
Mhm.
Now, if the target volume were 15 instead of 25, now my actual volume is bigger than my target volume. In this case, I have 21 minus 15 is 6. And so that squared, 6 squared is 36 times 2 is 72. So if the target volume were 15 instead of 25, my volume energy would now be 72 instead of 32. And everything would reverse. I would reduce the energy then by shrinking rather than by growing. And if I had 15 voxels, then my volume energy would be 0. Thank you, John. So here are those calculations done out. And I didn't make it's easy enough to make an I skip or an arithmetic error where you're off by 1 or something like that. But in fact, in this case, I got it right. Problem 2 was a little bit more complicated. It was a different shape. And now I said you have a surface constraint as well as a volume constraint. And this is to try to help you begin to think about how surface constraints and volume constraints interact with each other. And I promise you I won't make you do this analytically more than once in this one homework problem. It's not something that I expect people to go and count everything by hand all the time. But I think the exercise of doing it once is probably not terrible. And so here we said the target volume is 15 and the target surface is 13. So how do I evaluate this? Well, the first thing I have to do is I have to evaluate what the actual volume is. So I count the number of cells, the voxels. And I have to get what the actual surface is. So I have to count the number of edges of the pattern. And then what's a single voxel change to make and then once I have that, I take the difference between the volume and the target volume, square it, multiply by the constraint. I take the difference between the actual surface of the target surface, I square it, multiply by the constraint, I sum it up. Now, the second thing is, the first question is then, is the actual volume bigger or smaller than the target? My actual volume is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So my actual volume is bigger than my target volume. So if I lose a voxel, I reduce my volume energy. What about the surface area? Well, let's find a place where we can start. I'm going to start from this edge. 1, 2, 3, 4, 5. Oops, I'm going to get lost. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So my surface is 28. 28 minus 13, 15. 15 squared, 225. 225 times 3. So the surface energy of this is much bigger than the volume. Now, if I want to reduce the total effective energy, getting rid of a voxel, if I pick the right voxel, if I get rid of a red voxel, it automatically reduces the volume. Can't not reduce the volume. But I could get rid of a red voxel that actually increased or didn't change the surface area. For example, Suppose that I pick this voxel on the top right corner here. If I made that white, I wouldn't change the surface area. The number of edge voxels wouldn't change. So getting rid of that voxel would reduce the volume energy, but not the surface energy. On the other hand, this guy here at the top that I'm pointing at, that one at the top left has 3 white neighbors. And if I got rid of it, I would lose 3 white neighbors and gain 1. So I'd lose 2 neighbors. I'd lose 2 units of surface. So getting rid of that top left one would reduce both the volume and the surface. And so both of those energy terms would go down. And so the system is going to preferentially get rid of voxels that have high surface compared to high volume. So both the volume and the surface will shrink, but the surface will shrink faster than the volume. Is that clear? Okay. Is this trivial, or is this something that's worth going over? I don't know how people feel about if it's obvious to people, we could go faster. But if you haven't done these calculations, it feels a bit funny to be counting 1 through 21 in a class. On the other hand, maybe it's worth seeing it once to get a familiarity with it. Has anybody done this kind of exercise on Manhattan metric geometry before? No? So I guess it's just, you didn't read Mathematical Games. Well, probably you weren't born, some of you weren't born when that Mathematical Games column was written, but those of us who are older, I guess, could read it. I never thought when I read it as a teenager that I would actually be using it 40 years later, 50 years later. Okay. So then it says, was there possible configuration that would minimize the total effective energy? And is the total effective energy 0? And that was a little bit of a trick. And I don't remember the answer in this particular case. In other words, is there some way of arranging 15 voxels so that the total perimeter is 13 or less? If there is, then you can have a total energy of 0. If not, you're stuck. And so if I have 15 voxels, the most compact configuration I could have would be a 3x5 brick or a 4x4 square with a corner chopped out. A 4x4 with a corner chopped out has a perimeter 4 plus times 4 is 16. Chopping the corner out doesn't change it, so the perimeter is 16. So for a volume of 15 voxels, the smallest possible surface area is 16. So the answer is no. There is no configuration where the energy is 0 in this case. I can make the volume energy 0, but I can't make the surface area energy 0 if the volume is 0. So I have a choice. Either the volume is going to be bigger than the target, less than the target, and I can satisfy the surface constraint, or the surface will be bigger than the target, and then in that case I can satisfy the volume constraint. I can't satisfy both constraints at once. In this case, because the strengths of the constraints are 3 and 3 respectively, I'm going to split the difference. If one of the constraints were stronger, then I'd push the system towards having the right volume and not the right surface, or the right surface and not the right volume, depending on which was bigger. Okay. And then we talked about dynamics a little bit last time. And we talked about how cells really have motors that move their surfaces around actively. We simulate that as quasi-random force fluctuations. And the result is that the velocity of a cell is proportional to the drag times the velocity of the cell is proportional to the force divided by the drag. And we talked a little bit about the algorithm that's used. We pick a lattice site at random. We pick one of its neighbors from our neighbor list at random. we evaluate the change in total pattern energy by making the copy. If the total pattern energy goes down, we make the copy. If the total pattern energy goes up, we make the copy with a probability that's proportional to that delta H divided by the fluctuation amplitude. And again, we could argue that it may not be quite the right form, but that does have the result, if we do the math, that the velocity is proportional to the force. And then we had a homework problem where we had a cell with only a volume constraint. And what happened when we did that homework problem? Emma says the cell turns into dust because there's no constraint on the surface at all. One thing we might want to remember, which I talked about briefly last time, is how that initialization works. We've just added some better initializers to CompuCell, courtesy of Peter Fife, who was actually a student who took this course last year and stayed on and worked with us to improve CompuCell after he did his degree. We're very grateful to him for doing that. But in general, CompuCell doesn't have a lot of initial condition generators. It has the ability to draw a box, a square of squares or rectangles, and a quasi-circle, what are called blob initializer and uniform initializer. And we don't have a huge amount of flexibility within that. What we can do is we can define the corners of our box, min and max, box min and max. We can define the size of the squares that we're going to draw, which is called width in this case. We can define a gap, which is a spacing between our cells, which will be filled with medium, or whatever we had before. And we can say whether we want only one cell type or multiple cell types. If we list multiple cell types, they're going to be randomly positioned. And one thing that's sometimes a little bit of a convenience feature is that if we list the same cell type twice, we get more of it. So if we listed types mesenchymal, comma, mesenchymal, comma, epithelial, we'd get 2 mesenchymal cells for every epithelial cell. Now, if we want fine-grained control of our configuration, we should probably draw it in Python more strictly. But that's a little bit of a game one could play if you want to change ratios in initial condition. The drawing algorithm isn't very smart, and so sometimes you'll have a situation where the cell will protrude a little bit, or it'll be smaller than it should be. In other words, if I define a box that's 49 by 49, so exactly 7 cells fit, 7 by 7 cells fit in it, I'm fine. If my box isn't divisible by the size of the cells, then either the cells will be truncated or they'll actually overrun the box size a little bit. It's not a very bright algorithm. It would be nice to have an algorithm that filled in random, spatially relaxed cell shapes instead of squares. So one of the things we'll find in simulations is a lot of times we'll create one of these artificial initial configurations. We'll run the simulations for a little while to eliminate the graininess of the initial configuration and then start the simulation for real. A blob initializer basically looks the same, except it draws a rough circle. We specify the position of the center and then a radius around the center, and then it draws squares in just the way the other one did as well. And in that case, you always are going to get stair-stepping at the edges. In either case, you could draw a single cell by making the size of your box smaller than the width, or in this case, the radius a little bit less than width over 2, if you want. Both blob initializer and uniform initializer, you could have multiple instances of them in the same simulation. So you could draw a rectangle here of cells of one type and another rectangle of cells of another type. In general, with XML, the sequence of lines doesn't matter. Blob initializer is one of the cases where it does. And so the blob initializer calls are done sequentially. And so if you have a pattern that overlays another pattern, it will overlay it. So one thing that I could do with a uniform initializer, I'm sorry, blob initializer, is if I draw a circle of cells and then I overlay it with medium, a circle of medium, I could get a ring of cells, an approximate ring of cells. And so I could use successive calls to blob and uniform initializers to draw slightly more complicated initial conditions. The current version of CompuCell has some fancier initial condition generators for generating tubes and spheres, things like that. They're a little nicer than these older ones. And I don't have slides. If somebody wants to play with those, they're described in the readme for the new release. I haven't had a chance to play with them yet. Would be interesting to try them out. Okay. So yes, for the homework 2 problem, the behavior of cell with only volume constraint was basically our cells turned to dust, which we saw. Now, the third problem, we created a simulation with volume and surface constraint. Initially, we said that the target volume and target surface were both 25, and lambda volume and surface were both 2. And I said, what did you see, and can you explain the difference from the previous result when there was no surface constraint? And then I asked people to try a high target volume, high target surface, high target volume, low target surface, low target volume, and high target surface, and low target volume, low target surface. And I said, well, what do you mean by low and high? And we talked about that a little bit. And that extra problem was really about that Euclidean case. Does anybody want to tell me quickly what they got or show us what they got for that homework problem 3? So Emma says that when you had she had a target volume of 25 and target surface of 25, she didn't get single voxel dust, but the voxels coalesced into clusters. But didn't keep the cell coherent as a single cluster. Now, if you keep decreasing the target surface, then effectively you're penalizing having the cell broken apart because small clusters of cells have bigger surface area than a single big cluster. And so if you keep lowering the surface compared to the volume, it'll force the cells to stay coherent into a single cluster. If you make the target surface too small compared to the volume, then effectively, again, it's like a beach ball with a lot of air compressed into it. The cell will get very rigid. It'll get square and rigid. Similarly, if we make the volume very large compared to, the target surface very large compared to the target volume, then that's going to tend to want to create more surface, and it'll force the cell to fragment, and it'll push our dust, make sure that our dust really stays dust-like and has the voxels separated from each other. Something that's sort of interesting to look at is what the actual volume is compared to the target. So in that case, if we play with the lambda volume, if lambda volume is much bigger than lambda surface, then the cells will try to satisfy their volume constraint and ignore the surface constraint. If lambda volume is much less than lambda surface, then the cells will satisfy the surface constraint and ignore the volume constraint. If the target volume is very big compared to target surface, the cells are floppy or sinuous or dust-like if they fall apart. If target volume is much less than target surface, then the cells will be stiff. And I say round, but round in this funny lattice world means square, at least for nearest neighbor surface calculation. If we had longer range surface calculation, then the cells really would be round. So that's a place where it really makes a difference, to Pedro's earlier question. Okay. And so the other thing we had to think about was these fluctuation amplitudes relative to all these energies in our system. And we had already looked last week at these simulations that Julio wrote for us, where we have a cell crawling and behaving reasonably well, and another cell that's crawling and turning into dust, falling in pieces. A cell sorting simulation where the boundaries of the cells are relatively well behaved on the left, and then on the right, one where the blue cells, the boundaries are falling apart with respect to each other, and the green cells, the energies are so big that they're basically lining up on the lattice. And so generally we want cells to stay relatively connected. It's not terrible if they have an occasional stray pixel, but they shouldn't fall apart into two completely different domains. And boundaries should be fluid. Cells should move freely, but they shouldn't crumple up into that sort of disordered pattern we see in the top right. Now, of course, biologically, they're counterexamples to almost everything. And so sometimes the cells really do get rigid and square, and sometimes the boundaries of Vox cells really do get interdigitated and messy. And so in those cases, we might use values of parameters that we wouldn't use normally. But a typical cell boundary is not interdigitated, and it's not dust-like. And so, again, as pathologies go, if the fluctuations are too small compared to the effective energy, then the cells won't move, and we'll see alignment with the lattice, which is always a pathology because nature doesn't really have a lattice. And we'll see sharp corners in our cells. If the fluctuations are too big compared to the effective energy, then cells will split into multiple domains. We'll see a lot of stray voxels, and we'll see boundary boundaries crumple. And again, in years past, I didn't really harp on this so much early on in the class. And then people would come to me in week 5 or 6 stuck because they'd have problems and they wouldn't know how to diagnose them. And so I decided that this year I would emphasize some of these pathologies early. I realize until you face them in your simulations, they may not be as meaningful, but I hope then at least you have some way of debugging your own simulation. Okay, so let's now do a simulation. I've talked a lot. Let's set up a basic simulation template. So if I could ask people to fire up CompuCell, give people a minute to do that. Give me a thumbs up maybe when you've got it ready. And I want you to create a new CC3D project. Jonathan says he's ready. Kyle, you've got CompuCell running now? Pedro, I don't mind. I know you've got it. Jonathan, Alex, how about you?
Yes.
Okay, Emma. Okay, so let's create a new CC3D project. Give it a name. You can see that these slides were when these slides were written and for what, because the thing that's typed here is CC3D 2022 workshop, but you give it some name that's more meaningful to you today. And we're going to accept our basic simulation template. We're not going to change that. We're going to create a single cell type. So in the cell type specification, you type the name of the cell, hit add, and then continue. We're going to skip the chemical fields for this today. And then we're going to give the cell a contact energy, a volume, and by default center of mass is selected. So a neighbor, I think, is selected too, so you don't have to change this. But do click on the contact and the volume flex boxes here. Okay. And then hit done. So did everybody have that work? Okay. And why don't you run the simulation and see what it does? And you should get something that looks like this. So let's see if that works. I realize I'm merging, but I was merging multiple slide decks together for this lecture because things are slightly out of phase from the way I did it last year. And so there was an extra slide in there. There may be one or two places where there's some glitch because of the merge. In which case I appreciate your patience. Did you get something that looked like this? Everybody, Jonathan says yes. Alex, did that work for you?
Yes.
Okay, Pedro. I think Pedro, you didn't you write this lecture? So no, this is Julio's slide, I think. At some point, you're going to see Pedro's names on some of these slides because Pedro actually gave some of these lectures last summer. He's been writing some new material for this class. Emma, did that work for you? Great. Okay. So one thing that we can see if we do this in steps is that initially we have squares, and the squares gradually rough up. And as time goes on, over short time, we see some relaxation of the shape of the individual cells. They get to be a bit more or less hexagonal. And then it takes longer for the array, which was initially square, to round up. So there are two time scales here. One is a short time scale where the edges of the cells individually equilibrate. And then there's a longer time scale where the whole structure rearranges. And that's actually very typical of the biology. You get short range relaxation of over short times, and then it takes longer for the whole thing to reorganize itself. So I'll remind you that, and this is, Julio likes Macs, so he's got the screenshots for Macs, and it's going to be slightly different on Macs and PCs. We have that tools button here, which has this funny notation of a wrench and a screwdriver, which may not be the most obvious mnemonic for adjusting the color display of your simulation. Maciek liked to have sort of joke icons. It's like having a floppy disk, an old-fashioned hard case mini floppy disk as your way of saving, as an icon for saving things. But in any case, that will pop up this preferences window, and you can change the colors of your cells, the boundary colors, and so on, as you like. The way that plays out is slightly different on a Mac and a PC, but just to remember how to do that. You do have to remember to hit OK if you want to accept the changes that you've proposed for the colors. Okay. One thing that you might want to think about is, and you'll get these kinds of questions a lot in homework, and it's something that I think that we don't teach and learn very well in a lot of classes, is you'll get a question of describe what you see. And that kind of open-ended question can be challenging. And it's not that one has to write a PhD thesis about what you see, but it is asking you to pay attention to what's going on. And so if I were to ask you what happens in this particular simulation, I would say, well, at the beginning, the cells are squares, which is not biologically natural. And then I see these small deviations from their squareness happening very early in the simulation. And then pretty quickly, the cells lose that square geometry, that vestigial square geometry, and become more fluid-like, more hexagonal as it happens. And then there's, as I mentioned, this longer-term relaxation of the shape of the whole array, the shape of the aggregate, which loses its square shape. And so that would be what I would hope that you might say you'd see if you were asked to describe what happens in the simulation. So short-term cells relax to equilibrated rounder shapes individually, and then longer term, the tissue rounds up. And in this case, both of these happen because of the contact energy, which is an energy function that we've mentioned before but haven't really discussed. And so I'd like to talk about contact energy. Contact energy in some ways is very simple. In some ways, it's a little more complicated than the constraints we've dealt with so far. And the way contact energy is specified in CompuCell is based on sort of physics ideas and some history, and may not be the most natural thing if you're coming from biology. So contact energy is an energy that depends on the surface, like the surface area constraint, but the energy contribution per unit surface isn't just a number, which is the area. It's the area times the energy per unit surface area, and that energy depends on what is on either side of the boundary. So if I have two things that stick to each other, the energy per unit contact area of something that sticks is negative. Bringing them together reduces the energy. So that's got a negative contact energy. If things repel each other, then I have positive contact energy. And so there's a matrix J which specifies the energy per unit contact area between all pairs of cells. Now, if I only have one cell type, there are only two contact energies that matter, the energy between cell and medium. If I have more than two kinds of, if I have additional kinds of cells, then I'll have additional pairs. So if I have, say, 3 cell types, I'd have energy between cell 1 and cell 1, cell 1 and cell 2, cell 1 and cell 3, and cell 1 and medium. Cell 2 and cell 1, and so on. It's symmetric. The energy between cell 1 and cell 2 has to be the same as cell 2 and cell 1. So I have an upper diagonal matrix. And then I'm counting the surface area, but I'm weighting it by the energy per unit surface area. And in this case, I almost always use a interaction range that's longer than 1, typically 3 or 4. So if I want to evaluate the contact energy in a longer range lattice, it's a little bit more work, and I have a little example worked out. I'm not going to assign that as a homework problem. So I have to pick, so how do I do it? I pick all voxels of a cell. For each voxel, I have to find all voxels in different cells within the interaction range. I have to check what the type of that cell is, of the neighbor, and then I have to add that number up. So suppose I have the configuration here that I show here. I have 8 cells in this picture, actually 7, no, 8, because 7 is sort of off on the corner. And suppose there are 4 types. Cell 3 and 4 are type A, cell 1 and 5 are type B, cell 2 and 6 are type C, and cell 7 and 8 are type D. Now I pick a voxel. Here I picked this voxel that belongs to cell number 3. and that cell is of type A. And now I look at its nearest neighbors. I'm going to just look at its nearest neighbors for the moment. Its nearest neighbors are here. I have two neighbors of type 3. Well, there's no boundary between the cell and itself, so that has an energy of 0. But I have two neighbors that are of type 6. So I have to look in my table. I have cell 6 is of type C. So I have 2 units of boundary between A and C. So I have 2 times JAC. Fortunately, you don't have to do this by hand. CompuCell does it for you. But again, I want to walk you through what that plug-in is actually doing. So I have 2 units of A plus AC. Now I pick another voxel in my cell. Here I pick this voxel here, 3. So I'm still of type A. And now somebody tell me how many nearest neighbors do I have that are not of my own type, in my own cell, sorry, for 3, this one. Pedro? 1. The only nearest neighbor that I have that's a mismatch is the 5. And it's of type B. And so that gives me a JAB. Okay? You can see why you wouldn't want to do this by hand. And now I do it again. And if we went to second neighbor, well, here my second neighbors are that initial voxel. So now my second neighbor includes my 2 6s that I had before, another 6, and now a 5. And so now I have 3 JACs and 3 JACs and 1 JAB for second neighbor. Again, you could argue that those longer range ones should actually be down-weighted by the distance. Be interesting to study them. And so you get that. And maybe people don't feel like doing this in detail today, but let's suppose let's just have people try it on their own. Pick this voxel number 2. What's the contact energy associated with that voxel, the highlighted voxel number 2, if we do nearest neighbors? Well, let me do the nearest neighbor one first, out, and then you can think about the second neighbor. The first neighbor, I have 1 neighbor of 2, 1 neighbor 2. Those don't do anything. 2 to 3. 2 is of type C, 3 is of type A, so that gives me 1 JAC. And I have 2 and 4. 4 is of type A, 2 is of type C, so that gives me another JAC. What does the second neighbor, somebody want to walk through the second neighbor for that voxel? Alex, can you do that with me?
We'd have like BC, is that how you do it?
So who are my next neighbors? I have second neighbor would include this 1 and this 4, as well as that 4 and that 3. So if it's a 1, I have to look up. I have a 2 next to a 1. A 1 is of type B, a 2 is of type C. So that gives me a JBC. And what about 2 and 4? What about that?
That'd be an AJAC.
Yep, that's right. So again, when you do it the first time, it's a bit clunky, but if you do it a few times, you'll get used to it. Okay. One of the things that we did, and it was the extra homework problem, and I'm not since we're a little behind, I'm not going to run through this, but let's just think about what's called scaling. I mentioned before, if I have a shape and I expand or contract the shape while keeping the shape the same, the area of the shape will go as the square of the length. The perimeter will go like the length. So if I double the size, the area will go up by 4, the perimeter will go up by 2. And I mentioned that we could calculate what we call perimeter volume or surface area ratios. And in Euclidean space, that's easy to do for a square or for a sphere. And you'll get particular ratios that for those. The square, in the case of a circle, you'll get the ratio is going to be square root of pi. It's a little messier algebraically for a sphere. On a lattice for nearest neighbors, it's easier to do. If I have a square, the volume is 1, and the surface was 4. We calculated that. If I had a 2 by 2 square, the volume is 4, and the surface is 1, 2, 3, 4, 5, 6, 7, 8. The surface is 8. And so the volume went up by 4, and the surface went up by a factor of 2. If I go by 3 by 3, the volume is 9. The surface of a square of 3 by 3 is 4 times 3 is 12. And so you'll see that the volume scales as the square of the length, but the surface area doesn't. The surface area doesn't increase as fast on a lattice as it does in Euclidean space. And if you do that in second neighbor, it gets a little more complicated. You do it in 3D, it's also different. And so the surface to volume ratios on a lattice don't behave the way they do in real space. Okay. Let me just talk a little bit more about contact energy. The contact energy is specified in the XML. There's a plugin called contact, and you specify essentially that array of pairwise contact energies. So you'll have energy between medium and medium, which we don't, oops, sorry. Medium and medium doesn't really exist because there's only ever one medium cell. So you could give that any value you want. Then you have a contact energy between medium and your cell type A, your first cell type. That number is meaningful. Then you always are going to have an energy between the cell and its own type. So even if you have only one cell type, you're always going to have 3 lines. Medium to medium, which is blank, doesn't do anything. Medium to cell, and cell to cell. And then that neighbor order, which is pretty critical, and by default it's set to 4 in the simulations. Now, in reality, cells are more complicated than this. Cells have cell adhesion molecules on their surfaces, and the cell adhesion molecules bind to molecules on the other cell. And the binding energy depends on the type of the molecule and the density of the molecule. And so there's a plugin called Adhesion Flex that lets you implement that mathematically, where you say each cell has a density of particular molecules, and then you define a formula that says what the adhesion energy per unit area is, given the density of molecules on cell type 1, on cell 1 and cell 2. Why would you want to do that? Well, if all of your cells of a given type are identical, then this formalism we have on the screen is fine. But just the way we might want the cells to grow, in which case the target volume would change. And we can't do that if all cells have identical target volume. In the same way, biologically, a cell might change its type or density of a particular molecular species. You might increase the number of N-cadherin and decrease the number of E-cadherin. You might start adding cadherin 8 or NCAM to the cell. And so you might have two cells that are of the same type, which have the same adhesion molecules on their surface, but the densities are different. Or the cells might move the adhesion molecules from one region of the cell to another. So the adhesivity would be different in different surface parts of the cell. And so for all of that flexibility, we could use that adhesion flex plugin. But for the moment, it's a little more complicated to think about that. It's not rocket science to do it, but we already have to keep track of a bunch of adhesion energies. And when we start using adhesion flex, we now have to keep track of molecular species and the map between molecular species densities and the adhesion energy. And so we're not going to use that for the moment. But if I were going to do something like trying to explain metastasis, where the cells are individually changing their density of certain kinds of adhesion molecules, then I'm going to have to use a more complicated formalism. So sometimes we're stuck. Sometimes the biology requires us to do slightly more complicated mathematics. Okay. Last time we also talked about steering while a simulation is running. If the parameters are specified in the XML, then we can change the values on the fly as they run. When we get to Python specification, we're also going to find that we can change the values on the fly as the simulation runs, but it's a little bit different how we do it. The one thing that we have to remember is that if we start out with a float in the steering panel, we have to type a float. So if it was 2.0 and we want to make it 3, we have to type 3.0, not 3. And if it started out as an integer like 25, we have to type 26, not 26.5. That's a weirdness about the way the XML parser works. Okay. So in our simulation, we had two cell types, medium and bicell here. And our contact energy matrix had three unique terms: medium, which doesn't do anything, cell medium, which we can change, and cell, which we can change. And so really we only have two significant values, cell, and cell medium contact energy. And so I'd like people in the simulation to go into the XML or into the model editor, either way as it's running, and change the medium cell contact energy, which by default is set to 10, make it 20. And tell me what you get. How does the simulation change? Emma says she thinks the cells may be changing more quickly when we change the cell medium contact energy to be larger, but she's not sure how to quantify it. If we change the cell medium contact energy, the cost of cells touching the medium is bigger, and effectively what we're doing is we're compressing our aggregate. So it's going to be trying to minimize its surface more than it would for a smaller contact energy. In my experience, making that particular change doesn't do a huge amount. Here I'm walking through the steps that if I did it in parallel, and I've changed it in the XML as opposed to changing it on the fly. But and remember that if you change it in the XML, you have to save it, and the player, if you hit stop and start, it should reload the new version of the simulation. So we talked about, so if you're going to steer it, let me just walk you through steering for the XML for contact energy. One, the model editor steering in player is nice, But when you open that model editor, initially all of the plugin parameters are the trees are closed. And so you have to open them up to be able to see what's going on. So here, when you open the model editor originally, you'll see something that looks like this. It'll say pots, plugin cell type, plugin volume, plugin center of mass, plugin contact, steppable uniform initializer. So I'll have to open the plugin contact. And then really the display is not as convenient as possible. It'll say energy 10, energy 10, energy 10, but it won't tell you which energy it is. It would be nice if it displayed that in that property column there. And so I have to open those up too, and it'll say cell type 1, medium to medium, cell type medium to my cell, and so on. So now I know which 10, and which 10 those are. So now I know if I want to change cell medium, I have to change that 10 there. Okay, to 20. And since it was a 10.0, I have to type 20.0. And then I hit play again to run it. And so if I increase the contact energy, you should get something that looks a little bit like this, where the system is a little bit more round. Is that what Emma more or less what you got? Yeah, it's a little bit slow. The fluctuations here are not very large compared to the energy, so the system is a little bit stiff. Okay. So if I compare the 10 and 20 case, the surface is smoother because the cost of that surface is bigger. So fluctuations on the surface are more expensive. And it does round up a little bit faster because the forces I'm applying to it are bigger. If I want to think about cell shapes, in reality, cells have all sorts of diverse shapes. Some of those shapes are going to be rather hard for us to deal with here. In principle, we can have very complex shapes, but in practice, when we want to make very complex shapes, we need a lot of voxels per cell. And so if we're going to have very complex shapes, we're not going to be able to simulate very many cells at once. But two of the fundamental cell types that we're going to deal with, which I mentioned before, are mesenchymal cells and epithelial cells. Mesenchymal cells, it's a little bit of a cheat because depending on how we look at them, they have different shapes. If we look at them from the top or from the section, they have different shapes. But epithelial cells fundamentally are cells that are packed together into layers. And as always, biology has lots of different kinds of examples of this. In simple epithelia, you have a single layer of cells. In complex epithelia, so a simple epithelium might be the gut, the lining of the gut, for example. In complex epithelia, you have multiple layers. Stratified epithelia, you have multiple layers of cells. Sometimes those layers lie neatly on top of each other. Sometimes they mix into what are called pseudostratified layer epithelia, where there isn't so clearly layer 1, layer 2, layer 3. Sometimes the cells in the different layers have the same similar shapes. Sometimes the cells become more elongated, called columnar in biology. That name is pretty obvious. When the cells spread out and are flatter, the biological term for that is squamous, which may not be so familiar if you haven't done biology. So if the cell looks like a pizza or a puzzle piece, that's a squamous cell. If the cell looks like a pencil, it's a columnar cell. Mesenchymal cells are connective tissue, and while we think of ourselves as three-dimensional, and again, this takes me back to my childhood and watching science programs, which is that we think of ourselves as three-dimensional, but actually our bodies are mostly composed of layers of epithelia. Those epithelia may be rolled up into tubes, as in our blood vessels. They may be crumpled, as they are in our gut. But actually the amount of true three-dimensional tissue, as opposed to layered tissue we have in our bodies, is fairly limited. Now, some of those limited regions are pretty important, like the brain. Although the brain is actually sort of a funny mixture of epithelial and mesenchymal behaviors. That breakdown of epithelial and mesenchymal doesn't quite work when you get to neurons. But in general, in mesenchyme, cells are more separated from each other, and the cells are not as packed together, and they tend to have more rough surfaces. As always, there will be exceptions to this rule, but if I take mesenchymal cells, immune cells would be typical mesenchymal cells. Neural crest cells during development would be another example of that. And so we could get at least some elements of that in a simple simulation by controlling the degree to which the boundaries of our cells are rough and the degrees to which our cells are packed together or separated by space. So now let's go to the same simulation we just ran. We changed medium to my cells to 20. Now let's set it to 5. And before you run it, ask yourself, what do you think will happen when you make the cell medium contact energy 5, remembering that the cell-cell contact energy was 10? What do you think is going to happen? Try thinking it through in terms of energy. If the system is trying to minimize its effective energy, and you make the contact area between medium and my cells smaller, are you going to increase or decrease the amount of medium cell contact energy area? Jonathan? You're making medium my cell contact cheaper. Are you going to increase the amount of it or decrease it?
I would imagine you'd increase since it
That's
isn't
right.
as adverse to it.
Exactly. So you would expect that the cell medium contact energy will increase, and you could do that in a couple of ways, right? You could make the cell boundaries with medium wrinklier, or you could have the cells separate and disperse into the medium. Both of those will increase the amount of cell medium contact energy. If you set cell medium to 5, what happens when you run it?
Some migration of cell outward.
So Emma says that the cells migrate outward, they separate. And something like this, maybe? So the tissue doesn't fall apart immediately. It doesn't go boom and separate. But you do see individual cells wandering off. And that's because there's a little bit of a complication when we do cell medium versus cell-cell contact energy, which is that when we take two cells that are in contact with each other, touching each other, and pull them apart, we have twice as much cell medium contact as we had cell-cell contact. If we have the cells in contact with each other and we have 1 unit of contact area here, and I now pull them apart, we have 1 unit of contact with the medium from cell 1 and 1 unit of contact from cell 2. And so cell medium energy actually needs to be multiplied by 2 if I want to compare it to cell-cell contact energy. And so if cell medium contact energy is 5 and cell-cell contact energy is 10, then effectively the cells don't care energetically whether they're touching each other or the medium. What if you now make cell medium contact energy 3? I'm going to go off script, make it 3. Now what happens? Do the cells separate more or less than they did before?
Imagine more when we say it now.
Emma, what about you?
They separate more.
They separate more because now actually it's cheaper to have cell medium and boundary than it is to have cell-cell boundary. And so if I do, now notice there's another thing to notice that is that the medium is, the changes are happening at the surface. If I'm in the middle of a block of cells that are touching each other, and I change the contact energy with the medium, they don't know about that because they don't know anything about medium. The only place that the medium makes a difference is where there's medium. In some versions of this kind of simulation, you allow medium to get into the middle. You allow medium to show up anywhere. It's called heterogeneous nucleation. CompuCell doesn't let you do that. And so you'll see the medium, the tissue will gradually fall apart from the edges in. It'll crack, essentially, and separate when you make it 3. And so, yeah, this was the example here. And so if you wait long enough, you should see something like that. If you look at that bottom row, is that what you got when you ran it? Okay, so you'll get dispersal of the cells into the medium. And now you could try, if you do the steering, you could try putting that cell medium contact energy back up. Now what you should see is the cells wander around, but when they touch each other, they stick. And so you'll see clustering of the cells, gradual clustering of the cells. And they may come back into a single cluster or not, depending on the luck of the draw. A lot of people try that. So now you have a fairly elaborate set of control that you can do. You can have a tissue that becomes compact and round, or a tissue which stays compact mostly, but a few cells fall off on the surface, or a tissue that wants to fall apart and have the cell separate. So that's actually already a lot of control to get from changing that one parameter, which is the cell medium contact energy. Now there's something that we haven't talked about, which is if I zoom in and look at a single cell, then the roughness of the boundary of the cell is going to depend on the ratio of that cell medium contact energy to that fluctuation amplitude called the temperature. If the cell medium contact energy is small compared to that temperature parameter, then the cells are going to be fairly compact and polygonal. If the cell, sorry, it's said exactly backwards. If the cell medium contact energy is big compared to the fluctuation amplitude or temperature, then the cells will be fairly compact and polygonal. If I make the cell medium contact energy small compared to the fluctuation amplitude or temperature, then the boundaries of the cells will get rougher. And so I can control that as well. Now, I can go back, I could set my cell medium contact energy back to 10. And now let's flip it and change the cell-cell contact energy. So let's put the cell medium contact energy back at 10, and now set the cell-cell contact energy to 1. See what happens. And I should have probably had 1.0 in the slide because you have to type 1.0. What does it do? And as always, it's better if you could try to think about what you expect before you do it. And I'll try to ask that question. And I realize just the way the question, describe what you see, until you've done it a few times, it may not make sense to ask that question. But it's important, especially when you build more complex simulations as you go forward. It's really important to build an understanding of what you expect and why you expect it, based on the biology, what you know about the neural circuit, about the genetic circuits, about the signaling, about the forces in the system, about the energies in the system. Because if the simulation does something strange, you'd like to know that it's not what you expect. Sometimes it's not doing something that you expect because there's some emergent biological property that's very interesting, in which case you've discovered something. Sometimes it's not doing what you expect because you made a mistake. And you'd like to have some intuition about which of those two it is. And so asking the question before you make a change, what do I think might happen, is useful, especially in these very simple examples. So what happened when you tried a cell medium of 10 and cell of 1? What happened? Anybody?
The cells kind of bled into each other almost.
Yeah, the
Not
boundary.
directly, but they kind of wrapped around each other.
That's right. Now the cost of cell contact is very low compared to fluctuations. The cell boundaries are going to get basically just, you'll get things that look like puzzle pieces. Like that. You'll also find that the tissue is pretty soft now, and it rounds up very rapidly as a whole. And so this is a very fluid-like situation. Now, what if you go the other way? What if you make, now you've made the cell contact energy very small. Now bring the cell medium contact energy back down to match it. Make it 1. Maybe it should be 1/2, but try 1 first. So now cell contact energy is 1, cell medium contact energy is 1. What happens? This is a little, sorry, go ahead.
A lot of tissue becomes more ragged.
Right, so Emma says the border of the whole tissue becomes ragged. So yes, exactly. So the thing isn't rounding up anymore. It's basically, it doesn't care much about the cell medium boundary anymore. On the other hand, we still kept the cell medium contact energy. It's more than half of the cell contact energy. So this thing is still going to stay compact. The tissue as a whole can blob out, but it's not going to fall apart. If you make now cell contact energy, cell medium contact energy 0.3, what happens? 0.3. And again, I'm going off script a little bit. That's a little further on in the exercise stack. But what happens if you make it 0.3? Do the cells disperse now? Yeah, now the cells are ragged and they disperse. So, but even with the case that we had where we have cell medium equal to 1, cell equal to 1, cell medium equals 10, cell equals 10, we had very different geometries, even though the the cell medium and the cell contacts are the same, equal to each other. And that's because of the relation with the fluctuation amplitude. And so that comes back to what I was saying before. If the cell medium contact energy and the cell contact energy are both small, then the effective energies are going to be small, and the probability of accepting a copy is always high, whether that copy is favorable or unfavorable. If the cell medium contact energy and cell contact energy are big, then favorable updates are always made, but unfavorable ones are almost never made. And so that fluctuation amplitude is really important. The scale of energy fluctuations compared to that fluctuation amplitude temperature is critical. If those fluctuations, if the energy scale is big compared to fluctuation amplitude, then you'll get smooth boundaries. If the fluctuation amplitude is large compared to the energy scale, then you get fuzzing out and the system doesn't pay as much attention to the rules. Okay. So the last one we could do is try 2 simulations, and then we'll take a break. Cell medium contact, you've got cell medium and cell equal to 1. Now change the fluctuation amplitude, that T parameter, make it 1. And run it. Take a look at that, and then make cell medium equal to cell equal to 10 and T equal 10. And now ask the question, do the simulations of those two things, do they look the same or not? It's a little bit of a trick question because the answer I'm looking for here is not the is almost but not quite the true answer. Emma, did they look different or the same?
They looked quite similar to me, except maybe when you have these all set to 1, it's slower, but I'm not sure I trust them.
So Emma says they look quite similar to her, but maybe the one where they're all set to 1 is a little bit slower. So Emma gave the answer I wanted, which is they should be the same, because if the energies are multiplied by the same number as the temperature, the delta E over delta H over T is the same, so it should be the same. And that's true. The difference is that in this case, we changed the contact energies, but there's also the volume energy, and we didn't rescale the volume energy. And so when we reduce the fluctuations, the volume energy term is bigger compared to that. And so Emma is absolutely right. When you make T equals 1, effectively the volume energy has been increased and the system becomes stiffer and it updates slower. And that was precisely the thing that I was expecting Pedro to overthink. And Emma got me on that one, which is great. So I appreciate that. So the simulations look like this. They both give you the same shape. But because the volume energy wasn't rescaled, the one with T equals 1 takes longer to get to that final configuration. If you divided lambda volume by 10 from its initial value, then they would be exactly the same. So you could try that. So in the J medium equals 1, cell equals 1, T equals 1, find whatever the value of lambda volume was, divide by 10, and then you should get exactly the same thing as 10, 10, 10. So try that out. Okay, so you've actually, again, I realize that we've spent a lot of time on things that may seem artifacts or the basics, but I think if you've done these, if you've got this sense of how things change as I change relative values of energy and fluctuate relative values of energy compared to fluctuations, what seems like a normal or desirable behavior of cells versus one that's not desirable, like falling apart. If you've got that intuition in these very simple cases, now when you go forward to more complex situations, you'll be able to say, gee, this is something that's an artifact of the way the simulation is written. It shouldn't be doing this. And I hope you'll have an intuition about how to diagnose those kinds of problems. Because these aren't syntax errors kind of problems. They're not going to generate errors in the code. What's going to happen is you pick parameters that aren't doing something that's biologically meaningful. And so I'm trying to help people come up with some intuition about what makes sense in terms of simulation behavior. So let's take a break. Let's come back at 7 o'clock. Let's come back at 10 past 7, and we'll come back to that cell sorting exercise and spend a little time on that, okay? So everybody stretch your legs, get something, water, whatever you need, and we'll come back in a few minutes for that. And if anybody has any questions in the chat or in the room, you're welcome to do my best to answer them as we're here. Last time we started on the cell sorting exercise, but we didn't really process it very far. And so I'd like to do I'd like to do a little bit of play with the cell sorting exercise based on what we've understood for single cell types. Okay, so remember that cell sorting comes from a very fundamental biological observation. The first biological observation is that we have layered structures in the body. we mentioned the organization of epithelia into stratified epithelia, where we have layers on top of layers. And one of the questions is, how do we maintain these relative organizations of cells in stratified epithelia? And this kind of layered architecture shows up repeatedly in developmental biology in particular. In adults, where the epithelia have tight junctional structures, the maintenance of the epithelia is a little bit easier to understand, perhaps. But in early development, the things that are going to form epithelia later on tend to have rather mesenchymal cells. The cells are able to reorganize more fluidly. And so in those situations, you don't have the junctional structures that maintain epithelia in adults. And so again, we're coming back to this old biological observation of Malcolm Steinberg, that if we treat cells as fluids by taking cells and dissociating them and then mixing them together randomly, we see sorting, where if we have two cell types, typically we'll get one of the cell types going to the center of a blob and then be surrounded by the other cell type, if we do this in suspension culture. And again, this is an experiment we used to do in my lab, the old days. And we also find that pattern of sorting behaves as if there really were a surface tension. And you could even estimate the surface tension. Foti and Forgox built a little device where they'd make a sphere of a given cell type, and then they'd press on it. When you press on a sphere, you stretch it so it has a bigger surface area. And so you could measure the energy required to create that extra surface area, and that gives you a rough estimate of the surface tension, which is where these surface tension dynes per centimeter come from. And what they found was that always when you combine two cells, with the one with the higher surface tension goes to the center and the one with the lower surface tension goes to the surface. And the original version of that experiment was done with cells that you didn't need to label fluorescently, like the pigmented neural retinal cells of the eye. And in this case, we could follow it in time more easily. And we see that in this case, the black cells, which are the pigmented retinal cells, initially are dispersed. Already by that first picture, they've clustered a little bit. And then you get gradual coalescence of the clusters. And if you wait long enough, all of the black cells will be in the center. There are always a few stragglers that don't behave the way they should, but almost all the black cells go to the center. And almost all of the white cells go to the surface. And in these experiments, over the time scale over which you do the experiment, there's almost no cell division, there's almost no cell death. There's effectively no cell differentiation. And as far as you can tell, the cells are all pretty much identical. All the epithelial, all the neural cells are pretty much the same. All of the pigmented retinal cells are about the same. There's always going to be some variability between cells. They're never two cells of the same type are never exactly the same. And as I mentioned before, there are other mechanisms which can give rise to cell sorting. And that's actually a set of sort of interesting demos one could do using other mechanisms to show how you could get sorting as well. If one of the cell types sends out a signal that attracts cells of its own type through diffusion, then you could get sorting through chemotaxis. If the cells send out Philipponian pull preferentially on cells of their own type, that could give sorting. And that really does happen in certain kinds of embryos. Differential contractility is a little bit harder to implement in CompuCell. So that first one is a little harder to test in CompuCell. So again, coming back to these ideas, Today we did some hand calculation of contact energy. So now maybe coming back to this picture today, having talked about it earlier in the class, this picture will make more sense. If we have our two cells that are surrounded by medium, we can ask how much contact do we have between the cell and the medium? And we'll just do nearest neighbor. Well, each of our yellow cells has 4 medium contacts. So we have 1, 2, 3, 4, 5, 6, 7, 8 yellow cells. 8 times 4 is 32. So we have 32 units of cell medium contact and 0 units of cell-cell contact. So the energy of this pattern is 32 times J cell medium. Now, that's the most cell medium contact energy we could have. Now, if I rearrange it to make as close to a square as I can, I haven't changed the total area, but now I can count, start from the notch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units of cell medium contact. And the internal ones are a little harder to count, but they're 10 internal boundaries. And so I've gone from 32 J cell medium to 12 J cell medium and 10 J cell cell. So it's minus 20 J cell medium, the change, plus 10 J cell cell. Remember before we had the factor of 2 for cell media versus cell cell? Here, the rearrangement, we lose 20 units of cell medium and we gain 10 units of cell cell. That's exactly that factor of 2 we were talking about before. And so now the question is if minus 20 J cell medium plus 10 J cell cell is less than 0, then I'm going to favor being compact. If it's bigger than 0, I'm going to favor spreading out. And so I can now reason on these patterns. This is what I'm talking about, thinking about what you expect to see before you do it. This is reasoning about these patterns to try to think about what you expect. So now suppose that I have 2 types of cells. Well, within the aggregate, type A versus type B behaves just like cell versus medium did in the previous example. But I have the complication that I now have the boundary of the cell with the medium. And so I have 5 contact energies here. AB, AA, BB, A medium, and B medium. And so if I think about these abstract checkerboard patterns, I can reason about what pattern would be the one that has the lowest energy. And then I can check whether my intuition is right. Notice that the reasoning about which pattern has the lowest energy tells me that if I run the simulation for a long time, that's what I expect. It doesn't tell me how fast I expect things to change. So this is the simulation which you've seen before of cell sorting. And this is a very simple simulation, but one actually sees some interesting things in this. If I run it again, one of the things you see is that initially the cells clump up. The green cells will clump up with each other. The blue cells will clump up with each other. And then as the clusters get bigger, the speed of movement of the clusters gets slower, and the time for the clusters to come in contact with each other gets longer. And so the initial clustering is quite quick, and then it takes a long time for the fluctuations to be big enough that that green cluster in the middle finds the edge. Once it touches the edge, there's rapid reorganization, but it takes a long time to find it. And this is typical if you've done chemistry and you've looked at activated processes. You know that the time for a chemical reaction depends on the energy barrier. And you've seen the rate of the chemical reaction before. The rate of the chemical reaction is given by the e to the minus energy barrier divided by T, which is precisely the function that Boltzmann factor that we used in our acceptance function for our algorithm. And what that means is that as energy barriers get bigger, it takes exponentially longer for things to happen. And so if we want our green cell cluster to cross a barrier of blue cells, as that barrier of blue cells gets thicker, things slow down a lot. In this case, the fluctuations are pretty big, so that the thing runs in a reasonable amount of time. The other thing you'll see is that at the end of the simulation, you might expect that you really have a concentric pair of cell types, so that the blue cells cluster is right in the middle of the aggregate. But if you actually calculate the energies, you'll find as long as the blue cells are compact in roughly a circle, where they are within the green doesn't change the pattern energy. And so there's nothing that pushes the blue cells to the middle, per se. The fact that they tend to go really to the middle in the experiment suggests that there may be something other than the pattern energy at work. Differential contractility, probably in that case. Okay, so why don't we try this? This is a little bit of an exercise for you. You did this last week, but see if we could do it again. In this case, I'm going to see how you can handle the wizard. Use wizard, create a simulation, keep your initial conditions, your default conditions, create two cell types. Classically, we called them dark and light, but you could call them cell type A and B. You want contact energy, volume, no surface energy, just contact energy. You could use blob initializer instead of uniform initializer. Things will behave a little bit better in that very first screen. No chemical fields. And try that and see what happens. So when you've built that by itself and run it, tell me what happens. Give people a few minutes to try.
James, I could ask a couple questions.
So Kyle wants to ask questions. Sure, go ahead and I'll repeat them for the people online.
When you say plug-in, what is that from computer science, or is it just a method or a different version of a part of the code? What is it?
So Kyle asks, what is a plug-in? And the answer is a plug-in is a technical term from computer science. Specifically, when you are constructing simulations in you're constructing code in C++, you can pre-compile the code and then have the modules attached to each other and linking as the dynamically linked libraries.
Okay. Yeah.
And so a DLL component is called the plugin.
Okay. And then the blob is just, you're meaning it's in an amorphous shape or something.
So
Not a computer science term.
So the blob initializer versus uniform initializer, as I mentioned earlier in the class, CompuCell doesn't give you a lot of built-in functions for creating initial conditions. Essentially, our two choices are to draw a circle or to draw a square. And we can fill that circle or square with either a single cell type or a random mixture of two or more cell types. And the cells can either be touching each other or separated from each other with a gap. So that's, in this case, we could start with a square of cells instead of a circle of cells. But the final configuration is a circle, and the simulation will run a little bit faster and be a little bit easier to interpret if our initial pattern is more circular than square.
So it's kind of a preset thing.
Right, so this is just defining the initial pattern of cells
Okay.
that we're going to use in the simulation. It would be nice if we had lots of interesting geometries to start with. And as I say, the new version of CompuCell's added a couple of those. But normally we could either read in a file which has a predefined set of initial configuration that we want, is one possibility. Or we can use Python to draw some complex shape that we've predefined. CompuCell lets you read in an initial configuration file. We haven't done that because we don't have any initial configurations to read in that we're using, but if we have some, if we digitize some experimental data set and turned it into something that CompuCell can understand, then we could read in that image and use that as the initial configuration.
Okay. Thank you.
Great, both great questions. So let people give me a thumbs up when they've got this basic thing working. Emma says she's got it. Jonathan, okay, everybody. What did you get when you ran it? The answer should be not much, actually. So the first thing is, let's look at the code. So let's look at the code. So the code looks like this. Remember how to open up the code in Twit. You double click on the name of the code, and that'll open up your windows, and then we'll look at the XML. The Python isn't doing anything in the simulation. So the first line will say CompuCell 3D. This is 4.4.0. Yours should say yours should say revision 2, version 5, 4.5.0, I think. And then there'll be this metadata block that basically talks about parallelization, which we're not using. And then that POTS block that talks about the size of the lattice. And then the volume, and in this case, by default, the volumes of the two cell types you've defined are the same. It's rather interesting to do sorting when the cell volumes are not the same. It behaves rather differently if the cell volumes are not identical. So if you're bored, you could try that one out. And then you're going to have a block which is called contact, which has that J, all those J terms. Mediums, medium cell A, medium cell B, cell A, cell A, cell A, cell B, cell B, cell B. And the default interaction range is 4, which we're not going to touch. And by default, it sets all of those energies to 10, which means that cell A and B are identical and nothing will happen. This thing will not sort. It won't do anything interesting. And so when we run this, and I say, now see what happens, does it make sense? I'll give away the answer for the first one. If the energies, the contact energies between A and B and BA are the same as AA and BB, the cells aren't going to sort out because basically the only difference is you've got all the cells are the same, but some are randomly one color and some are randomly another color. But behaviorally, they're identical. So there is no differential adhesivity here. The cell adhesion is all the same. So now try changing the contact energies. And here's a suggested one to try. Medium doesn't do anything, so you could set that to be anything you want. You might as well set to be 0 to remind yourself it doesn't do anything. And then set medium cell A and medium cell B to 16, AA to 16, AB to 11, and BB to 2. Why don't you try that and tell me what you get? And remember that a higher value here means less adhesion. So if BB is 2 and AA is 16, which one do you expect to have in the middle if it sorts? Ask yourself that question before you run it. If cell BB contact energy is 2 and cell AA contact energy is 16, which one sticks more? This one always feels a little bit backwards.
It's not intuitive.
Lower energy means more adhesion. So B sticks to B more than A sticks to A. And remember our experiment, the more cohesive cell type goes to the middle. So if you do this, you expect B to go to the center and A to go to the surface. Does it do that? Somebody try it and let me know. And if anybody's having trouble, implementing this example, let me know. Did it work? So you have to go into your model, you have to go into your editor and change just the values of the energies, these 1, 2, 3, 4, 5, 6 energy values. Alex, did that work?
I think so.
What did it do? Did cell type B go to the middle?
For the most part, or at least it's not on the surface.
Does anybody need more time? Is this working for people? Get something different? Yeah, depending on how big the simulation is, and sometimes it takes quite a while for sorting to happen. It can take 100,000 Monte Carlo steps. That early sorting happens quickly, and then it gets exponentially slow. So if you have a big simulation, and that's actually something that's observed biologically. And then I'll make a comment about developmental biology and biology in general. When I teach this course from a more biological perspective, perhaps, which is that very often in biology, especially development, you'll see two mechanisms that are at work doing the same thing. And the mechanisms will differ in the following way. One of them will have long interaction range and work quickly, but be only approximate. And then there'll be a second refinement mechanism that operates slower and over shorter length scales that cleans things up. An example of this might be the nervous system, where initially you'll get axonal projections all over the place, and then you'll get Hebbian pruning of the ones that you don't need and reinforcements of the ones that you do. In the peripheral vasculature, you'll initially get capillaries all over the place. Just as within the nervous system, the capillaries that have a lot of blood flow will get bigger and get reinforced. The ones that have relatively little blood flow will shrink and eventually disappear. In a lot of developmental processes which involve layering or sorting, you'll have a long-range mechanism due to either, usually due to diffusion, and then either chemotaxis or selective differentiation, where you'll get rough boundaries between domains and a lot of errors. And then you'll get cleanup of those boundaries either by differential adhesion mechanisms like this, or by selective cell death mechanisms, where if I'm cell A and I'm surrounded by cells of type B, I kill myself. That's another way to clean things up. And so those kind of mechanisms, you'll often get this kind of two-phase process where you'll get a coarse, moderately accurate, fast, long distance process, followed by something that works on finer length scales that refines that initial coarse pattern. And that kind of adaptation makes a lot of sense because we know that these systems are intrinsically stochastic and very noisy. Differentiation of cells is full of errors. Cells often misdifferentiate. So they don't read the differentiation information very accurately. And so you'll get a situation where most of the cells differentiate properly, but some substantial fraction don't, and you have to clean it up. Now, there are situations, and our colleagues at Purdue have done some beautiful studies of this, where the individual cells really do have to differentiate properly. So for example, in the hair cells of the inner ear, each cell has to exactly be right. And in that case, you'll get not one gradient that's defining positional information, but you'll get 6, 7, 8 different gradients. And they have very complex patterns of cross gradient activity to give accurate positional information even in the presence of large noise. And occasionally still you'll get mistakes. In humans, it's not unusual for humans to have an extra rib because the process that segments the body is not completely accurate. If you have one extra rib, it doesn't cause any problems. If you have 2 or more, then that tends to be a very serious birth defect. If you have 1, you wouldn't notice it. And it's sort of interesting because that segmentation process winds up being accurate to about 5%. And snakes have a lot of segments. And so 2 genetically identical snakes will have different numbers of ribs.
Is it bilateral?
So that's actually, Kyle asks, is it bilateral? And there's actually a really interesting question there because the segmentation is done separately on the 2 sides. And yet it's extremely unusual to have them not match. And it's not fully understood how information, if there is any information, crosses from one side to the other to synchronize between the 2 sides. This brings up a whole separate, probably not completely related, but fascinating question, which is, for example, if you look at your legs, you will notice that they're almost but not identically the same length. In early development, there is no signal between your left leg and your right leg that tells the other side how fast it's growing. And so it's been reasonably mysterious how size control of organs is specified. About 15 years ago, it was discovered that that there were 2 genes involved that were critical, called hippo and yap. Hippo, maybe for obvious reasons. I don't know what yap stands for. And that if you interfered with those, then size control of different organ systems was lost. But exactly how this works, what's upstream and downstream of them, and how they control patterning is not well understood. One of the things that was, I think, increasingly believed is that one way to measure size, and this would be, there's this beautiful lecture by Arthur Lander, which I recommend very much to people, that he gave at Banff a few years ago. It's available online, talking about size control. One of the ways you can get pretty accurate size control is, this is a little off topic, but since we brought it up, I'll talk a little biology, since this is a principle of biology course as well as an engineering course. Is if you generate a chemical in an early phase of development that has a very, very long lifetime, so it doesn't decay, and then you stop making it, then the concentration will be essentially inverse to the volume of the tissue. And now you have something that can basically measure how much the volume of the tissue has changed from the time you stopped making it. Now, if you only have one molecule that's doing that tracking, the accuracy that you see, say, between your legs is a bit surprising. But if you had 2 different chemical species that were fairly tightly controlled, then that may be sufficient to explain the accuracy of that left-right equivalence that we see. Exactly which molecules it is not so obvious, because you have to generate very uniform amounts to begin with, or you have to have some compensation mechanism so that there's some way of saying the amounts decreased by 50%, which is not so easy, although it's not impossible. adaptation. And so I think that the current belief of left-right rough symmetry in organogenesis comes about because there is some species that's generated that when that tissue starts growing, it stops generating that. And so then you can use that to measure the size increase. You have to have a very long-lived molecular species, though. And most proteins don't last long enough to have, say, in a human being, your legs are going to grow for 7 to 8, 10 years or more, 15 years. There are very few molecular species that have a lifetime of 15 years. And so then you have to have some way of maintaining that concentration over a long amount of time so that you can use it as a clock. And so I think there's still quite a bit of uncertainty at the molecular level about how these things are maintained. Accuracy in biology and measurement of large macro phenomena in biology is actually quite problematic. Cells know what their local environment is, but they don't, as I like to say, there are no roadmaps in biology. If you're a cell in a tissue, you know what your local environment is, but you don't have any concept of what's going on further than what you can see. And of course, by see, I mean touch and feel the direct chemical concentrations of it. And that makes the design principles, if there are any, if we want to talk about it that way, of tissues very, very different from engineered systems. Engineered systems, you can have a blueprint. There are no blueprints in biology. You build things from inside out. And so one of the complexities of doing the kind of work we do here is that we have to respect the information that cells really can have. Because we're not allowed to say, well, I want this pattern to be X, therefore I impose that pattern from outside. That's not how biology works. And so one of the things to me that's very interesting about development is how you build complex patterns without long-range information and without blueprints. And there are some very interesting principles about how this works, especially in noisy environments. And self-sorting is one of those very basic principles. It only works over fairly short ranges, but it's a very powerful fundamental principle which can give us refinement and clean boundaries between regions, which are otherwise hard to do. So did people...
It explains the smaller scale stuff, but not some of the things that might be regulated in larger.
So Kyle says we'll explain smaller scale stuff, but not so much larger scale stuff. So if you read, it's not fair because Walpert got sort of tarred with this, a caricature of his own idea. So if you read Walpert's famous developmental biology book, there's something called the French flag hypothesis, or positional coding, which says you have some long-range chemical gradient in the system, cells read the chemical gradient and then differentiate in response to the chemical concentration. It was shown, and Walpert already knew, that couldn't be right in most developmental systems. The noise, first, the chemical gradients in biology, most chemical species have diffusion lengths of 100 microns, 200 microns. And so you can't build a gradient that's centimeters long with chemicals in a simple through diffusion. So that's not possible. Secondly, if you have a shallow gradient, the noise of differentiation is so big that you're going to get misdifferentiation at the boundaries all over the place. And so the idea of concentrations giving positional information is not wrong per se, but it cannot be sufficient to explain compartmentalization and patterning that we see in large-scale biological systems. It doesn't work.
But there's got to be some kind of signal that happens, right? That starts at the smaller scale.
So
Or
Kyle
inhibits
right.
or
so Kyle says, well, there has to be some kind of signaling, and I don't know how much I want to do this and how much I want to finish our exercise, but I want to say maybe it's more important to talk about this. It's I think fundamental that one of the mysteries and interesting things that's happened in developmental biology in the past 20 years is that we've been able to, partly through simulations of this kind, quantitatively ask the question, are the mechanisms that have been hypothesized? The mechanisms are there. In other words, gradients exist, differentiation in response to gradients exists in biology. The question is, given the noise level and the gradients that exist, is the system accurate enough to produce the patterns that we see? The answer is no. By itself, those cannot be sufficient. And so then you have refinement mechanisms like apoptosis of cells surrounded by mismatched neighbors. You have refinement mechanisms like differential adhesion at boundaries that move cells that are just near the boundary on the wrong side across the boundary to the other side to clean up boundaries. You have these counter gradient systems that provide more accurate chemical positional information. You have contact induction planar polarity mechanisms that give you the effect of gradients, but not through diffusion, but through contact of cells. And so you effectively have much longer diffusion lengths for signals. So the answer is there are ways of building these mechanisms, but they're not the simplest ones that you might think of. And building simulations of this kind can help us ask the question. So far, we haven't really talked about what are reasonable values for these things that we're talking about, but especially when we talk about chemical diffusion and gradients, we'll really ask the question, there's a fundamental question, how far does the signal get? Who sends the signal? How far does the signal get? How accurate is the signal? How is the signal received? How do cells respond when they receive that signal? And asking those questions in a systematic way can really be enlightening because you discover that a lot of the ideas people had about how differentiation worked, how tissues were maintained, couldn't work.
They just weren't.
They were not physically realistic systems. In other words, that if you allowed arbitrary accuracy, arbitrary distance of signaling, then they weren't wrong in principle. But when you actually evaluated whether it was practical to do it, the answer was no, the error rates were too high.
So is there some correction going on in there then if it's?
So Kyle asks, is there some correction going on? And the answer is that I can't give you a general answer because in different situations, in different systems, you'll have different combinations of mechanisms working together to do this kind of cleanup. But again, if you're not a physicist, perhaps engineers like there to be a single mechanism, a single answer. In engineering, we love the idea, especially computing, we love the idea of orthogonality. You change one thing, you don't change anything else. Biology, because it's not designed, has no orthogonality. You change one thing, you change everything in the system. Because the system doesn't have to be explainable, it just has to work. And so you get these mixing of mechanisms. In this example of cell sorting that we're playing with, we're treating cell adhesion as if it's something that's independent of everything else in the cell. Well, in this case, we're not modeling anything else in the cell. But we're going to find pretty soon that cell growth and proliferation biologically are controlled, at least partly, by cell adhesion molecules. So the same molecules that are causing cells to stick to each other are sending signals to the cells that are telling them grow, stay put, or die. And so there's a mixing of mechanisms. It's very typical of biological organization that is not so easy to deal with when we're doing modeling. We'd like things to be separable. And when we're doing this sort of developmental processes, we're going to assume that things are separable. But we have to remember that that's for our convenience. That's for our attempt to understand these processes. We're simplifying things so that we can understand it. And we have to remember that biology may or may not really work like that. And there's some of these fundamental biological problems that I think, again, depending on who's in the class and what people's interests are, if people come from a very computing engineering background and we start talking about these evolutionary things, maybe sometimes it's not so interesting to people. If people come from a more biological background, then these may be the kinds of questions that you're really trying to get to with a class like this. Ultimately, again, we're dealing with vocabulary, grammar, conversation. This class this year has been sort of grammar first. I've been trying to show you the basic rules of things, and then we start talking and building. That may be more efficient if you're committed to learning how to do complex things in the long run. But it does mean maybe it's a little slower getting into the nitty-gritty of dealing with complex systems. So did anybody try this self-sorting example, and what happened? As we're almost wrapping up here. Did it sort? Did it? If we think about it, we could actually reason about it. In the case that I just showed you, you should have seen that the more cohesive cell type went to the middle, the less cohesive cell type went to the edge. And we're not going to have time today, but as an exercise, you could think about, suppose you wanted each one of the patterns that's on the screen here to be the equilibrium configuration. And you could ask the question, what is the hierarchy of those J's? In other words, if I have JAA, JBB, JB medium, JA medium, JAB, and I want this pattern, the pattern I've shown to have the lowest energy, what do the relative values of JA and B have to be? For example, suppose I want yellow in the middle and blue on the outside. Well, I need AA to be less than BB for that to be true. What about A on the left and B on the right? That's actually a little bit harder to figure out, although it does happen. What about B clustering but not completely separating from A? What would cause that? All of those, by the way, do happen biologically. And if you play with those contact energies, you can get all of those patterns as final states. So that's something that one could think about and try. Another thing that you could play with, and maybe this is the last thing to do, is if you go into your simulation and edit the line where you define the target volumes of your cells, and now make the more cohesive cell type half as big as the less cohesive cell type. Change the target volume of one of your cell types to be half of what it was before. What happens? Somebody try that. That'll be our last exercise. Another one that's quite interesting is asking this question about how long it takes for sorting to happen. We started out with a blob that was a particular size, make the simulation domain twice as big, make the blob twice as big. How long does it take for all the cells to sort out? Is it twice as long as before, 4 times as long as before? I already gave away the answer that when you make the system bigger, it takes a lot longer. But how much longer? You could do the simulation a quarter the size, half the size, twice the size, 4 times the size, 8 times the size. Get an estimate of how long it takes to sort in each case, plot that, and you can ask the question then, how effective is this mechanism as the system gets bigger? The answer is going to be as the system gets bigger, it gets less and less efficient. But how much less efficient? That's a sort of an interesting engineering question. And that could tell you something about how big the system could be biologically. Gee, we know that the sorting process has to happen in 4 hours because that's how much time the window is in development. So did anybody see what happened if you change the target volume of one of the cell types? What happened? Anybody have that result they want to show? So these are some other games one could play. It's actually rather interesting. If the cells aren't round, the way they sort is rather different. If the additional configuration is different, the way they sort is different. Anybody have an example they want to show? No? Somebody? Pedro, did you try one of those? What if you change the target volumes? Emma shared a picture. So Emma, you made the more cohesive cell type smaller, and you see then they have a hard time finding each other. So yes, sorting works pretty well if you have about 50-50 ratio of the two cell types. If one of the cell types is rare, it takes a long time to find each other because it takes a long time for cells to move through a tissue if they don't have any long-range information, if they're diffusing. Because diffusion, the time to go a given distance goes as the square of the distance, not linearly in the distance. And so if you double the size, it takes 4 times longer for something to find it. And so if you start out with equal fraction of the two cell types, sorting is faster. If you start out with, say, 20% of one cell type and 80% of the other cell type, the rarer cell type takes a long time to sort. So those are things that one could play with. There are other games we could play. And maybe we can set these up as a little bit of homework. If you have 3 cell types, you can get multi-layered structures. And of course, you have a lot more possibilities because you could have 2 cell types that mix and sort. A and B could mix with each other but sort against C. A and B could mix with each other and be outside of C. A and B could mix with each other and be inside of C. With 3 cell types, you can get really a lot of patterns, not just concentric rings, but all sorts of interesting patterns. And so 3 or more cell types, you can really get some very complex structures. And again, almost all of those structures are observed in some biological situation or another. And the last thing that I was going to suggest is trying this in 3D. The simulations are going to run a lot slower if I run a 3D simulation rather than 2D simulation. For the given, if the lattice is 256 by 256 by 256, it runs 256 times slower. But reorganization in 3D actually is easier than in 2D. If I have a barrier in 2D, and I have a cell here that wants to get here, the only way it can do it is break that barrier and reform the barrier. It can't know about what's happening around the barrier. In 3D, I can go around it. And so actually, cell sorting is a more efficient mechanism in 3D than 2D. And so I'd encourage you, and maybe I'll create, that's why I say I didn't know how far we'd get. I may give you a couple of very simple of these exercises as little homework exercises. I think given what you've done already, it's not going to be a lot of work to try those. And I hope it was okay for people to talk a little bit about biology and principles of organization. I realize some years people are really eager to get to complex simulations, and then they get pretty impatient if we talk biology in class. Some years, of course, people are more biological, and then they say, why are we doing all this computing and not talking about the biological principles? So I'll depend on you to give me some guidance. If I'm talking too much biology, tell me. If I'm talking too much computing and not enough biology, tell me. I'll do my best to try to adjust on the hoof to try to adapt to that.
Is the 3D more efficient because there's more information?
So Kyle asks, is 3D more efficient because there's more information? In a sense, you could say that. You can see around barriers more easily in 3D. There's the famous 19th century novel Flatland. And it's pointed out that in reality, you couldn't have life in 2D Because if you make a domain like a sphere, a circle, and you have a hole in it, a hole never heals up in 2D. Because the two pieces of the edge can't tell that there's a connection between them. And so surface tension, if you make a hole in 2D, you always retract. In 3D, if I have a bubble and I make a small hole in the bubble, it'll heal up. And so fundamentally, boundary crossing in 2D and 3D is different. And then there always are mathematicians or physicists who go the other direction and think about what would it be like in 4D. It winds up you couldn't have life in 4D either because things it's too hard to have. You need to have enough boundaries that you can define regions and not so many boundaries that you can't cross at all. And it winds up that 3D really has special properties mathematically compared to lower and higher dimensions. But that's a sort of a topic for the discussion over drinks, I think, more than anything else. But if you get a room full of really mathematical biologists, eventually you'll hear them talk about that. Okay, well, thank you very much, everybody. Appreciate you coming tonight, and we talk next week.